Hello everyone, I am Honardo, a PhD scholar from IIT Kanpur. I will talk about the week 6 fundamental of supersonic and hypersonic flow. We will discuss what was taught in this week, and if you have any doubt you can ask questions. So this is first question. The most probable macro state is associated with. If you have learned in the class, you might know what is the answer for this. What is the answer for this? Options are maximum number of microstates, thermodynamic non-equilibrium, thermodynamic equilibrium, maximum degeneracy. So the correct answer is maximum number of microstates. As all microstates are equiprobable, so the most probable microstate will have the maximum number of microstates. And it will happen only when there is thermodynamic equilibrium. So this C is also the answer. Now we'll see some theory. So what are the modes of energy for a molecule or atom? First, let's say for atom or molecule, there are 4 modes of energy: translational, rotational, vibrational, and electronic. These are energy levels for different modes of molecular energy. So, what is translational energy? Translation energy is when molecule have translational motion. So, let's say there is one molecule, it can move in any other direction. So, due to which it will have translational motion, translational energy. And one molecule can rotate about its axis. Let's say this is a diatomic molecule. It can rotate about its own axis. So it will have rotational energy also. And one in molecule, its both atom can vibrate. So something like a spring. Let's think like these two atoms are connected by a spring in a molecule. So this, like the spring vibrate, this molecule can also vibrate. So it will, due to its vibration, it will have molecule will have kinetic energy in this direction inside a molecule, and it will also have some potential energy. You can think of this like potential energy of the spring. So combination of these two will be the vibrational energy. As for the electronic energy, the electron rotates around the nucleus, so due to which it will have kinetic energy and potential energy. So combination of those kinetic and potential energy will be electronic energy. So this figure is for energy levels for different modes of energy. So in translational energy, the distance between different energy levels are almost same. For rotational energy, initially the energy difference will be low, then it will increase for the upper level. Vibrational energy, initially it will be high, then it will decrease. Electronic also, it will be initially very high, then it will decrease. Then the initial value will be higher than vibration. So from this you can see that also that to start the translation and rotational modes of energy, it will need very less energy, while for vibration and rotational energy it will need higher energy. This is for molecule. for the atom there will not be any rotational or vibration energy. There will be only translation and electronic energy. This you can also see that, let's say there is one atom only. There will not be any energy if it rotates about its own axis, because its moment of inertia is very low. And for vibration energy also, if there are no two atoms or more than two atoms, it will not move like a spring, so it will not have vibration energy also. It will not vibrate. So what will the total energy of a molecule? It will be the combination of all four energy. Epsilon dash equal to epsilon dash trans plus epsilon dash root plus epsilon dash vibration plus epsilon dash electronic. In the class, I am using the same symbols as in the class, so you might have already know what is the meaning of this dash. Okay, so let's say there is ground state energy which is given by epsilon dash 0 trans, epsilon dash 0 rotational, epsilon dash 0 vibrational, epsilon dash 0 electronic. So which is called 0 point energy, and for rotational the 0 point energy is 0. So what will the total 0 point energy? It will be the sum of all these 0 point energy, which is equal to epsilon dash 0 trans, epsilon dash 0 vibrational plus epsilon dash 0 electronic. Now we will see what is degeneration. So let's say we have some energy. So this energy can be in different energy states. Let's see this state 1, state 2, state 3. This molecule have same omega, but this direction is different. So energy is same for it, but only thing is that this is the different energy state. So for any given energy level epsilon I dash, there can be a number of different states. This is for, let's say, some given energy and epsilon dash. So there can be different number of states that all have the same energy. This number of states is called the degeneracy or statistical weight of a given level epsilon I dash, and is denoted by Gi dash. So the possible number of this number of states which have the same energy level is called a degeneration, and is given by Gi. Now we will see what is macro state. So consider a system consisting of fixed number of molecules n. Let's say there is n molecule in one system. And let Nj be the number of molecules in a given energy level epsilon dash j. Their energy level from 0 to j. 0 to some energy level till the infinity, and Nj is the number of molecule in energy state epsilon j dash. So let's say epsilon 0 dash will have n0 molecule, epsilon I dash will have n1 molecule, and so on. For total number of population is given by n equal to sigma j nj, and here nj is called the population of energy level epsilon j. If we look at our system of molecule at one instant of time, we will see a given set of Nj. That is a certain population distribution over the energy levels. It is called instantaneous population distribution or macro state. This is macro state. So let's say we are seeing this system. So in this system, some will have we will have one set of Nj value. Like N0 is one value, N1 is one value, and so on at one instant of time. That is called instantaneous population distribution. Now, what happens that these molecules are colliding with each other. So there will be energy exchange between them. So due to the exchange of energy, the Nj population will change. So we'll get a different set of Nj. And this different set of Nj is called different population distribution or macro state. So we get different macro state at different instant. So in this manner, over a period of time, one particular macro state which implies one set of Nj will occur much more frequently than any other distribution. This is called the most probable macro state, and it occurs when the system is in thermodynamic equilibrium. It is related to question which we have seen before. So now we know that what is the most probable macro state and when it occurs. And the distribution at that time is given by Nj star for the equilibrium. At an instant of time, the way, now we will see how this macro state are defined. So at an instant of time, the way molecules are distributed in different energy states define a micro state. So let's say we have 5 molecules and 2 energy states, FLM0 dash and FLM1 dash. 2 energy level we have, and N0 have 2 molecules and N1 have 3 molecules. Degeneracy of 0 energy state is 4, and for degeneracy of 1 energy state is 5. So how can we distribute these N2 and 3? So first energy state we can distribute like this, 2 molecules, and second we can distribute like this. Similarly, we can distribute in different degeneracy state. So we'll get a different microstate. So how we are distributing will give a microstate. And for the bosons, which I will tell you what, we can distribute in single degeneracy states also, multiple molecules, which will give a different microstates. So like this, we get the microstate. But these are the different microstate, but these are the same macrostate. Because why? Nj is same. Nj is not changing. Nj is same. Only the how it is distributed in a energy level is different. So this is the same microstate. So, and all these microstates are equiprobable. It means that the probability of occurring these microstates are same. So all microstates are equiprobable, and change occur in microstate due to collision. Microstate change due to collision. Let's say in our example only, if we are going from microstate 1 to microstate 2, we are not changing. The microstate will remain same, but our microstate is changing, and it will happen due to collision only. So there will be one microstate which has the most number of microstates become the most probable microstate. So if we see the number of microstate versus the most probable microstate, then we'll see that at a particular macrostate we'll have the most number of microstate. That will be the most probable macrostate. So we'll see the question. Uh, Someone joined. So if you have any doubt, you can ask in week 5. Oh, sorry, week 6. So we'll see the question. Total number of microstates for a given macrostate for a boson is given by. So there are 4 options: pi j nj plus gj factorial upon gj minus 1 factorial nj factorial, and all the options are with some small changes. So what will the answer for this? This is, if you directly remember, then you might know that it will be pi j nj plus gj minus 1 factorial upon gj minus 1 factorial nj factorial. And in these symbols, this pi j is denotes to multiplication or product, and nj is the number of molecules in energy level FLMJ dash, and gj is degeneracy of energy level FLMJ dash. So now we will derive this formula. So first we will see what is boson. So for boson, the number of molecules that can be in any one degenerate state is unlimited. So let's say we have one energy state. So in one degenerate state we can fill unlimited molecule, but there is one limit. What is the limit? Let's say this energy state is for epsilon j energy level. So maximum number of molecule it will have Nj. So the number of molecule which we are putting will never be greater than Nj. It will always be less than Nj or equal to Nj. Now consider one energy level by itself, say epsilon j dash. This energy level has Gj degenerate states and Nj molecules. Consider the Gj states as Gj container diagrammed here. So here you might be seeing these panels. These are dividing making a different containers. So these are the containers: 1 container, 2 container, 3 container, 4 container, like this. Gj container. So these are Gj container, and these are these panels which are dividing this molecule. So in first container there are 3 molecule, second 2 molecule, like this. So if we keep this panel here, we will get a different distribution or different microstate. So here X is the molecule, and in one degeneracy state we are getting different number of molecules. So how many panels are there? If the Gj states are there, then Gj minus 1 will be the number of panels. So if a molecule is moved to another container, a different microstate will form. So we have to see the total number of permutation between this number of molecules and this number of panels. So if we move the panel, we get a different microstate. So the total number of permutation between X and panel is given by. So how can be the total permutation? Total number of molecule is Nj, total number of panel is Gj minus 1. So how can both be distributed? Nj plus Gj minus 1 factorial. So Gj containers are separated by Gj minus 1 partition. Now this partition are interchangeable. Like if we change one partition to other partition, it will remain same. So we have to divide it by Gj minus 1 factorial, because it partition can be permitted by Gj minus 1 factorial times. And molecules are also indistinguishable. Like if we change from one molecule to another, this microstate will remain same. So it molecules also can be permitted by Nj factorial times. Hence, the number of ways Nj indistinguishable particle can be distributed in Gj states is Nj plus Gj minus 1 factorial upon Gj minus 1 factorial plus Nj factorial. Now, this is for only one energy state, epsilon j dash energy level. If we want to consider all energy level, then we have to do the multiplication for each and every level. So total number of microstate in a microstate is given by W equal to pi j Nj plus Gj minus 1 factorial upon Gj minus 1 factorial Nj factorial. So this W is what? Total number of microstates in a macrostate. And this W is function of what? N0, N1, Nj and so on. This W is also called thermodynamic probability or measure of disorder. And one more thing, before we have seen that when the maximum number of microstates occur, it will be the most probable macrostate or thermodynamic equilibrium. So if we do the maximization of this W, we will get the most probable macrostate. So now we found for what happens for boson. Now let's see what happens for fermion. So the total number of microstates for a given macrostate for fermion is given by A equal to pi j Gj plus 1 factorial upon Gj minus Nj plus 1 Nj factorial. Second, Gj factorial upon Gj minus Nj factorial by Gj minus 1 factorial upon Gj minus Nj factorial Nj plus 1 factorial, and option D pi j Gj factorial upon Gj plus Nj factorial Nj factorial. And we already know what is Gj, Nj and epsilon j. So what is fermion? So in fermion, all the one molecule will occupy only one degeneracy state. It cannot repeat like boson. In one degeneracy state, there cannot be multiple molecules. So for this, like for fermion, only one molecule can be in any degeneracy state at any instant. So for this, what should happen? Gj should always be greater than Nj. Because if Gj is less than Nj, what will happen? It cannot be fermion. Consider one energy level by itself, say epsilon g dash. This energy level has Gj degenerate states and Nj molecule. consider Gj states as Gj container. So we have this Gj container. If let's say we have take one molecule, it can be put into one container. So there will be Gj base. One molecule we can put in Gj base. We can put it here, 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 here. So total number of bases Gj. Now, if we take the next molecule, so if let's say we put in one, if in this way we put one molecule. Now if we want to put other molecule, how many empty boxes are there? Gj minus 1. So Gj minus 1 base we can put the second molecule. Similarly, if we repeat this process, njth molecule can be put in Gj minus Nj plus 1 base. Hence, the total number of bases Gj into Gj minus 1 into Gj minus 2 and so on, Gj minus Nj plus 1. If we multiply and divide it by Gj minus Nj factorial, then we will get Gj factorial upon Gj minus Nj factorial. And this is for, we have not considered that about particles, and all the Nj molecules are indistinguishable. So they can be permuted in Nj factorial ways. So number of ways Nj indistinguishable molecule can be distributed in Nj can be distributed over Gj states is given by Gj factorial upon Gj minus Nj factorial upon Nj factorial. This is for one energy level. So if we are considering all energy level, the total number of microstates for a given microstate is W equal to pi j Gj factorial upon Gj minus Nj factorial into Nj factorial. So this will be the answer. So before this often gives the answer. So you can see that for boson and fermion, both are the different number of microstate we are getting for a single microstate. Now we will see for next question, and it is related to Boltzmann distribution. The Boltzmann distribution in terms of partition function Q can be written as Nj star equal to A Nq Gj e to the power minus epsilon G upon Kt B Q upon N Gj e to the power minus epsilon G upon Kt. Option C, N upon Q Gj e to the power minus epsilon G upon Kt. Option D, Nq upon Gj e to the power minus epsilon G upon Kt. So what will be the answer? It will be option C, N upon Q Gj e to the power minus epsilon G upon Kt. Now in this one, you see here, this N is the total number of molecules, Q is partition function, Gj is degeneracy, K is Boltzmann constant, and epsilon J is energy measured above 0 point. Now one thing to pay attention is epsilon J is different from epsilon J dash. This epsilon J is taken above the 0 point energy. It means that if from the epsilon j we remove the 0 point energy, then we'll get the epsilon j. And one more thing, this nj star is given for uh, most probable distribution, most probable macrostate. So before Boltzmann distribution, we will write the expression for most probable macrostate using Bose-Einstein and Fermi-Dirac statistics. This Bose-Einstein statistics is for bosons and Fermi-Dirac statistics is for fermions. So first we will see the Bose-Einstein statistics for boson. So the number of microstates in a given microstate is given by W equal to pi j nj plus gj minus 1 factorial upon gj minus 1 factorial into nj factorial. This we have already seen before in the derivation. Now we can take the log. So you can see this is the product. So after taking the log, it will become the sum. So log W equal to sigma j log nj plus gj minus 1 factorial minus log gj minus 1 factorial minus log nj factorial. So here we are in the nj is very greater than 1 and gj is also very greater than 1. For this here 1 we can ignore in both these terms. So why it will be? Because translation energy levels are closely spaced and can be grouped into number of degenerate states. So nj plus gj minus 1 equal to nj plus gj and gj minus 1 is approximately equal to gj. And from the Stirling's formula, which is for log of a factorial equal to a log a minus a, and here a should be large, should be greater than 12, which is already satisfied here because nj and gj are large. So using this above relation in log w, so if we first write this nj plus gj minus 1 as nj plus gj, and factorial will be given as nj plus gj log nj plus gj minus nj plus gj. Similarly for log gj minus gj log gj plus gj, and for log nj also minus nj log nj plus nj. So here minus nj and nj will cancel out and minus gj and gj will cancel out. And now we will write nj terms together and gj terms together. So this is nj term and this is nj term. So we will get log w equal to sigma j nj log nj plus gj minus nj log nj. Now gj term together, gj log nj plus gj minus gj log gj. We can take nj here common and gj here common, so we'll get sigma j nj log 1 plus gj upon nj. This we have used the identity log a minus log b equal to log a upon b. So we got this plus gj log nj upon gj plus 1. Now recall w equal to f, n0, n1, nj and so on. So to find the maximum of value of W, we take the differentiation of this d log W equal to 0. So from the chain rule of differentiation, from this for this function we will get d log W equal to dou log W upon dou n0 dn0 plus dou log W upon dou n1 dn1 plus so on dou log W dou nj dnj plus so on. So we can write this as sigma j dou log W upon dou nj dnj. So we have to find this term dou log W upon dou nj. So this was the log W. So if we take the differentiation of this, it is a summation of this nj in nj. So only for nj term, if we are taking differentiation with respect to nj, only nj term will remain and rest of the term will be 0. So we'll get dou log W upon dou nj equal to log 1 plus gj upon nj plus nj upon 1 plus gj. We are taking differentiation of this term. If we take differentiation with respect to nj, first term, then log 1 plus gj upon nj plus nj upon 1 plus gj upon nj minus gj upon nj square. Similarly for second term, gj upon 1 plus nj upon gj into 1 upon gj. So here this gj will cancel out. Here this nj will cancel out. And if we multiply this nj by gj inside, we will get this similar term. So these two terms will cancel out to each other, and we will get log 1 plus gj upon nj. So what will we get for d ln w? Sigma log 1 plus gj upon nj dnj equal to 0. So we have not two constants. First is the total number of molecules is constant, which is given by n. So sigma nj equal to n. If we take its derivative, we will get sigma dnj equal to 0. And second constant is that sigma f(j) dash nj equal to E, total number of energy. If we also take its derivative, we will get sigma f(j) dash dnj equal to 0. Now we will solve this problem by method of Lagrange multiplier. So let's say we have two Lagrange multiplier alpha and beta. So minus sigma j f alpha dnj equal to 0 and minus sigma beta f(j) dash dnj equal to 0. So if we add all the equations, we will get sigma j log 1 plus gj upon nj minus alpha minus beta f(j) dash dnj equal to 0. So from the method of Lagrange multiplier, this term will be equal to 0. So if we remove the log, we will get 1 plus gj upon nj equal to e to the power alpha into e to the power beta f(j) dash. And here this nj will be equal to nj star. Why? Because we have maximized the number of microstates. So nj star equal to gj e to the power alpha gj upon e to the power alpha e to the power beta epsilon j dash minus 1. This is for boson. Now we will repeat the same process for fermion. So for fermion, W equal to pi j, Gj factorial, Gj minus Nj factorial, Nj factorial. We will take the log of this, so product will become summation. So we will get sigma log Gj factorial minus log Gj minus Nj factorial minus log Nj factorial. So we'll use the Stirling's formula here also. So log a factorial equal to a log a minus a. So if we use the Stirling's formula, this log Gj factorial will become Gj log Gj minus Gj. This log Gj minus Nj will become Gj minus Nj. Log Gj minus Nj minus Gj minus Nj. And this log Nj will become Nj log Nj minus Nj. So if we put all this here, we will get log W equal to sigma j, Gj log Gj minus Gj minus Nj log Nj plus Nj minus Gj minus Nj log Gj minus Nj plus Gj minus Nj. So Gj will cancel, Nj will cancel. Now we will take the terms with Gj and Nj together. Okay, so first, similar to before, we will write the for most probable microstate d log W equal to 0, and before we have found d log W equal to sigma j dou log W upon 2nj dnj equal to 0. So what is dou log W upon 2nj? So now this summation has all terms for nj, but if we are taking derivative with respect to nj, only nj term will remain. So we will get minus log nj minus 1 plus log Gj minus Nj plus 1. So this minus n plus will cancel out and we will get log Gj minus Nj minus 1. So if we put this value in the d log W formula, we will get d log W equal to sigma j log Gj upon Nj minus 1 dnj equal to 0. We also have the same constant as before, which is sigma Nj equal to n and sigma epsilon j Nj equal to e. So if we use the same method of Lagrange multiplier, we will get sigma j log Gj upon Nj minus 1 minus alpha minus beta epsilon j dash dnj equal to 0. And from the method of Lagrange multiplier, this term will be 0, which is equal to log Gj upon Nj minus 1 equal to alpha plus beta epsilon j dash. So if we take it out of the log, then we will get Gj upon Nj minus 1 equal to e to the power alpha e to the power beta epsilon j dash. So if we take this one on that side, and then we can find Nj star equal to Gj upon e to the power alpha e to the power beta epsilon j dash plus 1. This for fermion. Now if we check for fermion and boson, in boson it was Gj upon e to the power alpha e to the power beta epsilon j dash minus 1, and for fermion it is Gg upon e to power alpha e to power beta fl and g dash plus 1. So only difference is between plus and minus between the fermion and boson for most probable macrostate. Now we'll come to Boltzmann distribution. So for the high temperature, molecular distributed over many energy level. So what will happen? Gj is very greater than Mg, and it means what? The states are sparsely populated. Hence e to power alpha e to power beta epsilon j dash minus 1 is very greater than 1, and e to power alpha e to power beta epsilon j dash plus 1 is very greater than 1. So we'll ignore this one. So for fermion and boson, for both case, we'll get the most probable distribution is Nj star equal to Gj e to power minus alpha e to power minus beta epsilon j dash. This is called the limiting case. This limiting case is called the Boltzmann distribution. Here beta equal to 1 by kt, and if we take the summation of this, n equal to sigma nj equal to sigma j gj e to power minus alpha e to power minus epsilon j dash upon kt, and then this will equal to n. This e to power minus alpha is constant, we can take it out. So e to power minus alpha will be nothing but n upon sigma j gj e to power minus epsilon j upon kt, j dash upon kt. Hence we will get nj star equal to n gj e to power minus epsilon j dash upon kt upon sigma gj e to power minus epsilon j dash upon kt. This is Boltzmann distribution. But now if you are seeing that before question, here it was in terms of Q partition function, and there was no dash in energy level. It means that energy measured was above the 0 point. So now we'll try to write this equation in terms of that. So this epsilon j dash is what? Epsilon j plus epsilon 0, which is 0 level energy. So if we write this as that, we will get n gj e to power minus epsilon j upon kt into e to power minus epsilon 0 upon kt upon sigma gj e to power minus epsilon j upon kt into e to power minus epsilon 0 upon kt. This epsilon 0 upon kt is same for each and every term, so we can take it out and this will cancel. This both will cancel. So we will get nj star upon n equal to gj minus gj e to power minus epsilon j upon kt upon sigma j gj e to power minus epsilon j upon kt. This term e to power g sigma j gj e to power minus epsilon j upon kt is nothing but q partition function, and so it will equal to gj e to power minus epsilon j upon kt upon q, where q is the partition function and q is given by sigma j gj e to power minus epsilon j upon kt. So now till now what we have seen, what is microstate, macrostate, different modes of energy, how this energy is distributed, what is boson, fermion, what is the most probable macrostate for both boson and fermion, and what is Boltzmann distribution. So now we will see the next problem. Specific internal energy is written as function of Q as often a RT dou log Q upon dou T at constant pressure, RT square dou log Q upon dou T at constant volume, RT square upon dou log Q upon dou T at constant entropy, and RT dou log Q upon dou P at constant temperature. We'll see this. So how is the internal energy given by? If it is given by E equal to sigma J FLM J and J star, and this is for equilibrium, and it is measured above the 0 point. We are not taking the dash part. So now we will see from Boltzmann distribution. Ng star is given by n upon q gj flm e to the power flm j upon kt. So E will be equal to sigma j flm j n upon q gj e to the power minus flm j upon kt. So this n and n upon q is constant. This you can take it out. So we will get E equal to n upon q sigma j gj flm j e to the power minus flm j upon kt. Now let's see this partition function q. So this q equal to sigma j gj e to the power minus flm j upon kt, and you can see that this is a function of volume and temperature. So let's say we are taking its differentiation with respect to temperature at constant volume. Then we will get sigma j minus, if we take its differentiation, we will get minus flm j upon k minus 1 upon t square gj e to the power minus flm j upon kt. Minus minus will become plus, and kt square is constant, so it will come out, and it will become 1 upon kt square sigma j flm j gj e to the power minus flm j upon kt. Now you see in this equation, this term is similar to this. So we can get sigma flm j gj e to the power minus flm j upon kt is equal to kt square dou q upon dou t at constant volume. Now we'll substitute this in the equation 1. So we'll get E equal to n kt square upon q dou q upon dou t at constant volume. Now this is the total energy, total internal energy. So to find it as a specific energy, we will divide it by m, mass. So if m is the mass of a molecule, then total mass of the gas is given by m into n. So if we divide by m into n on both sides, n will cancel, and E upon mn equal to k upon m t square upon q dot q upon dot t at constant volume. Now from the definition, k upon m equal to r, which is specific gas constant. So we can substitute this as this R, so we will get E equal to, and this E upon M is will become specific internal energy. So it will become E equal to RT square upon Q, dou Q upon dou T at constant volume. Now if you see this term 1 upon Q, dou Q upon dou T at constant volume, it is nothing but dou log Q upon dou T at constant volume. So we will get RT square dou log Q upon dou T at constant volume. Which is same as option B. So now we have found the specific internal energy for the molecule. Sorry, for the system. So now in the next question we have to find specific internal energy in vibrational energy mode. Before the energy was combination of 4 energy: translational, rotational, vibrational and electronic. Now we have to take only one portion of that energy. Before, the E which we have found was combination of translational, rotational, vibration and electronic. So now we have to find the vibrational part. So we will see. So one thing is that this Q, it is partition function, is given by Q translation into Q rotational into Q vibration into Q electronic. So log Q will be summation of all these: log Q translation plus log Q rotational plus log Q vibration plus log Q electronic. And the last question we have found already: E equal to RT square dou log Q upon dou T at constant volume. So if we substitute this log Q here, we'll get 4 terms here: RT square dou log Q trans upon dou T at constant volume plus RT square dou log Q rotational upon dou T at constant volume plus RT square dou log Q vibration upon dou T at constant volume plus RT square dou log Q electronic upon dou T at constant volume. For this first term, with considering Q trans is translation energy, a specific internal energy of with translation mode, and this Q rotational containing term will have E rotational, Q vibrational containing term is E vibrational, and Q electronic containing term is E electronic. So this internal energy is nothing but sum of all 4 energy. But our aim is to find E vibration. So E vibration is equal to RT square dou log Q vibration upon dou T. So we have to find Q vibration. So Q vibration is given by, we have seen the formula before, Q vibrational, Q equal to sigma Gj e to power minus epsilon J upon Kt. So here this J we are substituting with N vibration, and epsilon N vibrational is given by NH nu. So we'll substitute it here and we'll get sigma N equal to 0 to infinity e to power minus NH nu upon Kt. And for from quantum mechanics, Gn equal to 1. So the degeneracy of each energy level is 1 only. So Q vibration we got is this, sigma n equal to 0 to infinity to the power minus n h nu upon kT. Now if we take the sum of this, put 0 here, we'll get 1. If put 1 here, e to the power minus h nu upon kT, and so on. So like this, we will get this series 1 plus e to the power minus h nu upon kT plus e to the power minus 2h nu upon kT, and so on. If we consider r here equal to e to the power minus h nu upon kT and a equal to 1, we'll get series like something like 1 plus r square and so on till infinity, and its summation is nothing but 1 upon 1 minus r. So we get summation equal to 1 upon 1 minus e to the power minus h nu upon kT. Now we will find dou log q vibration upon dou t at constant volume, which is equal to 1 upon q vibrational into dou q vibration upon dou t at constant volume. So we will take the differentiation of this q vibrational, which we found here, with respect to temperature. So it is equal to 1 upon q vibration is nothing but this 1 minus e to the power minus h nu upon kT to the power minus 1, and its differentiation will be minus 1 upon 1 minus e to the power minus h nu upon kT whole square into minus e to the power minus h nu upon kT into minus h nu upon k into minus 1 upon t square. So minus minus will become plus, and the multiplication of these two terms will become, this minus minus will also become plus. So we'll get h nu upon kT square into e to the power minus h nu upon kT upon 1 minus e to the power minus h nu upon kT. So we can write this as this e to the power minus h nu upon kT will we can write this as 1 upon e to the power minus e to the power h nu upon kT, and we'll get h nu upon kT into 1 upon t e to the power h nu upon kT minus 1. Hence our p vibration will be RT square into multiplication of this term. So it will become h nu upon kT into RT upon e to the power h nu upon kT minus 1. Which is nothing but option D, h nu upon kT RT upon e to the power h nu upon kT minus 1. So like how we found this for vibrational energy, we can find this specific internal energy for different energy modes, like translation energy mode, rotational energy mode, electronic energy mode. And the main advantage of this internal energy is for finding the uh, different properties. Now we'll see the next problem. When translation and rotational energy modes are excited, the value of Cp for an atom will be A R by 2, B 3R by 2, C 5R by 2, and D 7R by 2. So we have to find Cp. So Cp equal to Cv plus R, and Cv is given by dou E upon dou T at constant volume. Now I told you before that it will be used for finding the different property. So we can find Cv directly from E, and E is given by RT square dou log Q upon dou T at constant volume, and log Q is nothing but log Q translation plus log Q rotation. We need only two modes, translation and rotation, so we are using these two only. And for this is we have to find for atom. So for atom there is no rotational mode energy, so log Q rotational will be 0 and Q rotational value will be 1. For log Q will be log Q translational. So we have to find only for E translational will be RT square dou log Q translational upon dou T at constant volume. So now we have to find this Q translation value. So Q translation will be given by sigma j, Gj translational e to the power minus epsilon j translational upon Kt. And it will be equal to sigma I e to the power minus epsilon I translation upon Kt. Here epsilon trans is given by n square h square upon 8m into n1 square upon a1 square plus n2 square upon a2 square plus n3 square upon a3 square. Here a1, a2, a3 are dimension of box or system, and n1, n2, n3 are quantum state translation. So Q translation is given by sigma n1 equal to 1 to infinity, sigma n2 equal to 1 to infinity, sigma n3 equal to 1 to infinity, e to the power minus h square upon 8m kt, n1 square upon e1 square plus n2 square upon et square plus n3 square upon e3 square. So that's why here degeneracy we have not written, because in this translation term itself it is giving the degeneracy equivalent. Now we can separate it for sigma n1, sigma n2 and sigma n3 term as product of this. So we'll get sigma n1 equal to 1 to infinity e to the power minus h square upon 8m kt n1 square upon e1 square into sigma n2 equal to 1 to infinity e to the power minus h square upon 8m kt n2 square upon a2 square into sigma and 3 equal to 1 to infinity e to the power minus h square upon 8 m kt and 3 square upon a3 square. So these three terms are almost same. So we'll find only for one term, which is sigma n1 equal to 1 to infinity e to the power minus h square upon 8 m kt and 1 square upon a1 square. Now we have seen before in the starting itself, the spacing between energy levels is very small for translation energy. So what we can do, this summation we can write in terms of integral. So, and this term h square upon 8 m kt a1 square, we can see all terms are constant only. So we will write it as a tau, one value tau equal to h square upon 8 m kt a square a1 square. So we will get this summation n1 equal to 1 to infinity e to the power minus h square upon 8 m kt n1 square upon a1 square equal to integration 0 to infinity e to the power minus tau n1 square dn1. And the value of this integral is given by 1 upon 2 under root pi by pi upon tau. And if we put the value of this tau here, we will get a1 upon h under root 2 pi mkt. Similarly, for other this expression, we will get a2 upon h under root 2 pi mkt and a3 upon h under root 2 pi mkt. So if you multiply all these three, we will get a1 upon h under root 2 pi mkt whole cube, a2 upon h into a3 upon h. Now if a1, a2, a3 are dimension of the system, so if you multiply these three, you will get the volume. So Q translation is given by 2 pi kmt upon h square to the power 3 by 2 into v. So log of this will be, log Q translation will be log 2 pi mkt upon h square to the power 3 by 2 into v, and we will write t and v terms separate. So we will get this equal to 3 by 2 log t plus log 2 pi mk upon h cube 3 by 2 into v. Now from this also you can see that from here itself, this Q translation is nothing but function of volume and temperature. So now if we take the differentiation of this term with respect to temperature, we will get dou log Q translation upon dou T at constant volume is nothing but 3 upon 2 into 1 by T. So E translation will get RT square dou log Q translation upon dou T at constant volume, which will be 3 by 2 RT. Now for atom, this E equal to E translation will be there, which will equal to 3 by 2 RT. So Cv equal to dou E upon dou T to the power dou E upon dou T at constant volume, which will be nothing but 3 by 2 R. So what will the Cp? Cp will be equal to Cv plus R, which will be equal to 5 by 2 into R. So now we have seen the internal energy due to translational energy and electronic energy. So let's see for rotational energy also. And this as this rotational energy will depends on the type of molecule. So we are seeing only for uh, diatomic molecule. So Q rotational is given by sigma j gj e to the power minus e epsilon j upon kT. And j is the quantum number here for rotational mode. And for gj is given by 2j plus 1, which is from quantum mechanics. So epsilon j is given by, and epsilon j is given by h square upon 8 pi square I j into j plus 1. This is also from quantum mechanics. Now we'll substitute this value in the Q rotational. So Q rotational will be equal to sigma j equal to 0 to infinity 2j plus 1 for gi gj into e to the power minus h square upon 8 pi square I kt into j plus 1. Now this constant term we can take it as a. So a equal to, we will take h square upon 8 pi square I kt. So our Q rotational will become integration 0 to infinity 2j plus 1 e to the power minus a j square plus j. And let's say take this j square plus j equal to y. So we'll get 2j plus 1 dj equal to dy. We'll substitute it here. So you will get Q rotational equal to integration 0 to infinity e to the power minus ay dy. And if we do the integration of this, we will get minus e to the power minus ay upon a 0 to infinity. And if we put the limits, we will get minus 1 upon a to the power infinity plus e to the power 0 upon a, which will be nothing but equal to 1 upon a. And value of a was h square upon 8 pi square I kt. So we will get Q rotational equal to 8 pi square I kt upon h square. If we take the log of this, we will get log Q rotational equal to log 8 pi square I kt upon h square, and we'll separate the term t with other constant, so we'll get log t plus log 8k square ik upon h square, 8 pi square. If we take its derivative with respect to t at constant volume, we'll get it as 1 upon t. So we'll substitute this in E rotational formula, which was RT square dou log Q rotational upon dou T at constant volume, which will give us RT. So now, if we write the CV in full form, which will be dou upon dou T at the summation of all the internal energy at constant volume, we'll get 3 by 2 R for translational, R for rotational, and dou E vibration upon dou T at constant volume plus dou E electronic upon dou T. This E vibrational also we found before, so you can just substitute this E vibrational from before expression and find the derivative here for CV. Like this, we can get the CV. And for electronic energy, there is no closed form expression is available for the electronic energy for Q partition function. So partition function is generally written as the sum of whatever was given you, sigma gi e to the power epsilon I upon qt, and in this one the spectroscopic data are directly inserted in the terms. To find the electronic. Now we'll see the next question. Identify whether the following two statements are true or false. Statement 1. Air is mainly composed of diatomic gases N2 and O2, and therefore at room temperature gamma equal to 1.4. Between the temperatures 600 Kelvin and 200,000 Kelvin at P equal to 1, the gamma varies as the vibration energy mode is excited, and it is function of temperature. So what is the answer for this question? So both statements are true, because at room temperature air will have only two energy modes, translational and rotational. So in this translational and rotational, combination of these two will be 5 by 2. CV value will be 5 by 2 R, because from the previous formula, CV value will be 5 by 2 R and CP will be CV plus R, so it will be 7 by 2 R. So ratio of CP and CV will be 1.4. So CV will be 5 by 2 R and CP will be 7 by 2 R or ratio of both will be 1.4. And when temperature is going to be more than 600 and 2000, the gamma will vary, because there will also be one more term, vibrational energy term, due to which gamma will vary. So E vibrational we have seen before, it was h nu upon kt into RT upon e to the power h nu upon kt minus 1. We can write it as h nu r upon k into 1 upon e to the power h nu upon kt minus 1. Now, if we want to find the Cv corresponding to this term, so it will be dou E vibrational upon dou T at constant volume. So if we take the derivative of this term, this is constant, it will come out, and this term will become minus h nu r upon k upon e to the power h nu upon kt minus 1 whole square into e to the power h nu upon kt into h nu upon k into 1 minus t square. Minus minus will become plus, and this h nu upon k t will become whole square here into r h square nu square k square t square. So it will become h nu upon kt square. This r is coming here into e to the power h nu upon kt upon e to the power h nu upon kt minus 1 whole square. So this is the function of temperature. So it will vary. So due to which Cv will vary with temperature. And if Cv is varying with temperature, Cp will also vary with temperature, due to which gamma will vary with temperature. So from this figure you can see gamma is varying with temperature. So if you see this figure, first the translational energy mode is excited. It excites in the initially only. You can see at 1 Kelvin only. And then around 3 Kelvin this rotational energy is also excited for the air. Oh sorry, this between this 1 to 3 rotational energy also start getting excited, and at 3 Kelvin it gets fully excited, and at the 600 Kelvin the vibration energy also start getting excited, and till 2000 Kelvin it gets excited fully. After that there will be electronic energy and other kind of electronic energy also. So like this we find the Cv. So now we have seen this. Now okay, so we will stop here today. We will discuss next week problem. If you have any doubt, you can ask in the next week also.